So good afternoon, everybody, and thank you very much for the introduction. I'd like to thank the organizer. It's a great conference. So indeed, what I'm going to focus here on these tutorials is to show that we've seen that we can use femtosecond light to manipulate magnetization, but we can also use electron pulses. And so we'll see that this kind of results can bring us towards ultra-fast spintronic. Because it's the third day of the conference, I don't think I have to go. I have little introduction. Okay, so we're here between magnetism, electronic, and the ultra-fast optic. I don't have to convince you that it's very interesting in terms of fundamental science. We're looking at fundamental timescale energy. And so all the questions is how do we transfer energy and angular momentum to all those paths in such a very short time. Okay, so let's come directly to the outlines of my talk. And so the goal of this tutorial is going to be to fill this short. Okay, we're going to look at three different types of magnetization manipulation: demagnetization, what I've called all optical helicity independent switching, so that you can switch the magnetization and the helicity does not matter. And the third one, where we can see the switching, all optical switching, but this is helicity dependent. So three different types of manipulation. And I added a fourth one where we look at domino motion using this femtosecond light. So I have 8 boxes here that I'd like to fill. So can we do that with femtosecond light? You already know the answer for a few of them. And can we do that with electron pulses, which duration are about 50 femtosecond. And of course, it's going to be quite material-oriented, but each time we have some result, we'll ask ourselves, does it help to understand the fundamental mechanism? Okay, so let's start with ultrafast demagnetization. As you all know, this field started in 1996 by this extremely nice result that we've seen many times. This is a pump probe experiment. So you pump with a laser, and then you can have a delay between the pump and the probe. And so you can observe this ultra-fast demagnetization. And so this result were obtained in the team of Jean-Yves Bigot, also with Eric Borper, and as we heard, they both passed away, which is really sad. And I'd like to pay tribute to both of them. All right, so what we first already filled here is that you can observe ultra-fast demagnetization using a femtosecond light pulse. It was also observed that you could obtain an all-optical helicity-independent switching, and this is one of the first observation, where you see that you send one pulse, you switch in one direction, and you send a second pulse, and you switch it back. And in order to make sure that you have all optical helicity-independent switching, you need to have both, because one pulse is not enough to prove it. For example, you can have demag field that will create such a reversal. This was only observed on gadolinium-based materials. So it was observed first on gadolinium and cobalt alloys, and we have seen from the group of Bert Koopman, also from the group of Jeff Borker, and that it could also be materials which are exchange coupled to some gadolinium and cobalt alloys. It can also be some materials which are not showing this all optical helicity independent switching, but you put some gadolinium on top and then you see it. Okay. And so what we have done in this field, and the only result that I'm going to show here, is that, as it was also shown by other group, you can measure this switching just using a whole bar. And this can be done 10,000 times. It's a very robust effect. Okay. Third type of all-optical helicity, the all-optical helicity dependent switching. So in that case, it was also observed first in 2007 in the group of in MANGIN. It was observed also for gadolinium iron cobalt alloys, but what we could demonstrate is that it's an extremely general effect. you can observe it for many different kinds of materials. Can be ferromagnetic, can be ferromagnetic, they can be granular, can be multi-layers alloys. I would say that any magnetic materials can show this effect as long as they are always thin enough so that they are not going to break into domains that would avoid you to observe this effect. So any material that we've tried, as if we were able to do it thin enough, we could observe this kind of helicity-dependent switching. So most of the measurements that have been shown is that you just sweep the laser on the surface and you do clearly see the helicity-dependence effect. And what was also proved is that this is a multiple pulse effect. You need several pulses in order to observe the switching. So we kept a static beam here, and you see that we need at least 200 pulses in order to observe the switching. And there are this has been also discussed, always you need several pulses. And so the question was then, what's the mechanism? And so I would have two families of mechanism. The helicity dependent could come from the difference of absorptions. So that's the magnetic circular dichroism. And basically, because with one helicity, you absorb more than with the other, the system is harder or colder, so you have a probability of being in one direction or the other, which is different, and that could explain the switching. And indeed, for this to explain the switching, you need many pulses. And by the way, this MCD, of course, exists. The question is more, is it really an important effect to explain the switching or not? Second one is more, I would say, the fact that light has an angular momentum, and so this angular momentum is transferred. So this has been discussed a lot by Peter on this inverse Faraday effect, the fact that you would have an induced magnetization, and this induced magnetization, once you come to a temperature close to the ordering temperature, would be enough to do the switching. What we have been doing in this field, and it's not yet published here, is worked on a cobalt platinum single layer. And what we try to do is we try to optimize this all-optical helicity-dependent switching. So what we did is that we kept this 5 kilohertz repetition, that's fixed. We changed pulse duration, fluence, and pulse diameter. That was basically the 3 parameters that we changed. Okay, the data that I'm showing here, this is for a constant fluence. So your laser has a constant fluence. And then you just change the pulse duration. So, okay, first we apply the field just to be able to normalize the saturated magnetization. If we have a 3 picosecond pulse, there is no switching. If we have a 2.5 picosecond pulse, there is the full switching of this cobalt platinum layer. If we go to lower pulse duration, you see...
Just to make sure,
yeah.
But this is with a high rep rate, so there's not a single pulse.
No, it is not a single pulse. There are many, many pulses here, and this is an important, thank you. We will come that we will look at the number of pulses later. But here, in fact, the image is done after 600 pulses. So you can say that basically we obtain this image after 600 pulses. Okay, and then if you go to a much smaller pulse duration, keeping the same fluence, then it's totally demagnetized. Okay, so we have done this kind of measurements for many different pulse duration, many different fluence and pulse diameter, and we could build this state diagram. So this state diagram is basically, we plotted the pulse duration, we plotted the fluence, and then we looked at, after, let's say, 600 pulses, what is the magnetic state. Of course, if you have a very low fluence and a large pulse duration, there's no effect, no switching. Of course, if you have a very large fluence and if the pulse duration is short, then you have demagnetization here. And then there's this area where we do see this all-optical helicity-dependent switching. And this is the curve that we obtain. What we can say is that it's clear that if your pulse duration is small, then it's more difficult to get the right fluence in order to see the switching. But there's always an area where you do see the switching. If your pulse duration is high, you can see that the area where you will have the switching is larger in terms of fluence. Okay, so this kind of state diagram, we thought that this could help us to determine the physics behind this. So one possibility was that what would be constant is the fluence. Whatever the pulse duration, you would have one given fluence where you would have the switching. But this is clearly not the case. So second thing, we thought maybe that's just the maximum intensity that matters. But as you will see, the maximum intensity for those points here change a lot. So then what we did is we just used this three-temperature model as it is available. We had the pulse duration and the fluence, and we could determine the temperature of the electrons, the spin, and the lattice. And so here you have to understand that this is those points where you see the switching. So there are different fluences here, and you can clearly see it because depending on the fluence, you see that the temperature of the lattice is different. Depending on the pulse duration and fluence, the temperature of the electrons also changes. But there's one thing that seems to be constant in this system, at least for the parameters that we put it in. Most of the parameters we obtain from literature is that you can see that the temperature of the spins always come to the same temperature, and this temperature is close to the Curie temperature of the system. So it looks like the system has to come, the spin temperature has to come close to the ordering temperature in order to observe the switching. And then, okay, so that's the state diagram. One other thing that we looked at, we tried to optimize in terms of number of pulses. Here, we limited the number of pulses to 50 pulses with a 2 picosecond pulse duration. And you see that we have a perfect switching in one direction, and then perfect switching in the other direction, and again perfect switching in for 50 pulses and 2 picoseconds. If we do 10 pulses, you can clearly see the helicity dependence, but already you see some areas which are not so nicely switched. But we significantly reduced the number of pulses here. Here we are close to 10 pulses. For example, we have now new data where if we are able to go to 2.5 picosecond, with 10 pulses, that's perfect. So I think we can go to a very low number of pulses. So of course, we tried with one pulse. And with one pulse, for a certain fluence, that's what we observed. And we think that this curve is very important and can exclude MCD, at least in this case. What you observe is that for a given fluence, you have, if it's linear, you totally demagnetize. If it's one helicity, you have 10% switch in one direction and 10% switch in the other direction for the other helicity.
Sorry, 10% in possibility or 10% in the area?
10% of the area. So, okay, yes. What I should tell you is how we did the measurements. In this case, we have a whole cross. So we're measuring the whole signal. So I cannot tell you what's the magnetic configuration. I cannot tell you if this is up and down domains, if this is half of it that I switch or not. But this is a large dot on a whole cross. Okay, the reason why we believe that we can exclude MCD is that since we are starting from a saturated state, if you send one helicity or the other, I do understand that the absorption may be different, but that would only bring to different demagnetization. But the fact that it's crosses, and so that there is switching, would exclude this MCD. And in fact, what's happening is that for low fluence, you see those three signals decreasing, and at some point, they come to the fact that the linear is totally demagnetized. Okay, so from those measurements on this cobalt platinum, where we try to optimize the number of pulses, we believe that we are favoring this explanation of this laser bringing heat such that the spin temperature reached a temperature close to the ordering temperature, and that when you reach this temperature, then some description using angular momentum transfer, induced magnetization, inverse Faraday effect is enough to break the symmetry and result in the switching. Okay, so that's the case of this all optical helicity-dependent switching. All right, now let's see another type of helicity-dependent switching, which is domain-wall motion. Okay, so in that case, okay, we create artificially a domain up and down, and we have, so the domain wall is here, and then we're going to shine a laser just on the domain wall. And you can, so that's before sending the pulse, and this is after the pulse. And again, this is a large number of pulses that have been used. It's not a single pulse, many pulses. And another thing is that the intensity of the laser is below the switching threshold. So if you would put this laser on a saturated film, nothing would happen. You would have no switching. And clearly, you see that the domain wall is moving toward one direction for sigma plus. It's moving toward the other direction for sigma minus. And so what we could understand is that this domain wall motion, first of all, you have to overcome some pinning. And this results from the balance of three contributions. Purely thermal temperature, temperature gradient that created by the laser, and this helicity effect. And so what we wanted to see is what the effect of each of those contributions. But clearly here you already see that we have an all-optical helicity-dependent domain wall motion. All right, so here we used linear polarization. That's in fact to see the effect of the laser, but without the helicity. So basically we are killing this helicity effect. Okay, and so here we have before exposure and after what am I doing here? Okay, so that's with the linear helicity, okay, got it. Okay, with the linear helicity, if you shine just on the domain wall, nothing happens. Or you may have sometime, if your domain wall is really not straight, it moves a little bit to reduce the energy. If we shine a little bit on the left of the domain wall, then you can see that this domain wall is going to move toward the hot part. If you shine on the right, then it's going to move toward the hot part too. So basically, with the linear excitation, you have a temperature gradient, and the domain wall is going to move toward the hot part. Now, if we put some, okay, sorry, it's wrong. If you put some helicity, and then instead of shining on the domain wall, but a little bit away from the domain wall, you see that your domain wall is moving, and it's moving further than the domain wall position. So you see that for on one side, it's not moving at all. On the other side, it's going to move much more than the position of the laser. And that's true for both helicity. So here we see a motion, not here. Here we see a motion, and we almost see nothing here, and you see the motion here. All right, so that's clearly showing that what's happening is that you have a competition between the thermal gradient that tries to move toward the hot part and this helicity that tries to push us with this helicity-dependent effect. What we did here, you know that to change the helicity, you just have to change the angle of a quarter wave plate, and that's what we did. So we go from linear to sigma minus, linear again, sigma plus, and you see clearly the displacement that's happening when you change the helicity. So you're clearly following the displacement of the domain wall is clearly following the helicity of the light. Okay, and that's clearly shown here by the fact that you have a competition between this helicity that pushed the dominant wall toward this direction and the thermal gradient that pushed it toward the position of the laser. Okay, so all this part now, I filled those 4 boxes, showing that with femtosecond light pulses, you can have those 4 kind of magnetization manipulation. So now let's see if electrons can do the job too. So this was a work that was started by Nicolas Berger, who is here in the audience today. And so the experiment is the following. So first, what we have done is we looked at cobalt platinum. Okay, so the idea is to look at cobalt platinum and a pump laser beam was sent on one side, and we probed on the other side. Okay, and all the experiments was just to change the copper thickness here. So we went to no copper, so that the light would directly interact with the cobalt platinum, and then we went to so much copper that there is no way that this light can interact with the cobalt platinum. So it has to be something else, and I'll give you the conclusion right now. This is hot electrons that are moving ballistically into the copper. What was also looked at is the absorption as a function of this copper thickness. And you already see that if you have a copper thickness larger than 50 nanometer, there's very little light that is interacting with the cobalt platinum. So if you go to 100 nanometer, it's clearly no light interacting with the cobalt platinum. So depending on the copper thickness, so the reference is 0 copper thickness, 80, and we went to 300 nanometer of copper, you do see, again, this ultra-fast demagnetization of the cobalt platinum. So you see that it's as fast as expected for the reference layer, and there's little change if you increase the copper thickness. The only thing that you can see is that there's a delay. You can clearly see that the demagnetization starts at a different time, and this time increases with the copper thickness. And there's also a broadening of this fast demagnetization. So we looked at both the delay by delta t0, sorry, that's the delay, and delta tau is the broadening. And we then plotted delta t0 and delta tau as a function of the copper thickness. And we could have some linear variation, at least up to 200 nanometer, which tell us that this is hot electrons that are moving ballistically into the copper. And if we look at the velocity, it's very close to the Fermi velocity. So there's no way it could be phonons or other thing that would be much, much slower. So here we have hot electrons interacting directly with the cobalt platinum, leading to fast demagnetization, as fast as it would happen with some light pulses. And then we could even calculate it. And so we have a pretty nice accord between theory and calculation and the experiment. And we basically could define 3 different areas. So below 50 nanometer, this is the change in the magnetization for different laser power. So we have really here a decay, which corresponds to the fact that light is being absorbed. But then when you reach 50 nanometer, there's no light that is interacting with the cobalt platinum here. So you have something that is more or less constant, which is the fact that you have those hot electrons that are moving ballistically into the copper. And then it's no more ballistic anymore, and you have a decay again after 200 nanometer. Okay, so then what's been observed is ultra-fast demagnetization in a similar way using electron pulses rather than laser pulses. Now, let's see if we can do basically the same thing on gadolinium and cobalt, where we could see helicity-independent switching. So the gadolinium and cobalt that were studied are 5 nanometer thick. We studied different composition around the compensation, because you all know that it's where this effect is observed. We could build this curve, so we looked at coercivity and magnetization as a function of the gadolinium thickness. We can clearly probe the compensation where magnetization tends to 0 and coercivity goes very high. Okay, we took those materials and then we did two kinds of measurements. Either we pump and probed on the same side so that the light would directly interact with the gadolinium and cobalt, or we pumped on the other side in order to have those hot electrons interacting with the gadolinium and cobalt. So we put it 80 nanometer, but we reproduced it for 150 nanometer. So in all those cases, there's no way that the light can interact with the gadolinium cobalt directly. It has to be, again, those hot electrons. We looked at here, this is result obtained with light only. This is result obtained with electron only. And we looked at that for 4 different compositions. Here is the compensation. So we send one pulse, a second, a third, and a fourth. So we clearly see this all-optical helicity independent switching. Those circles here is when we decrease the fluence. And we did the same thing in the case where the electrons are interacting directly. And you clearly see that for one pulse, you have switching. Second pulse, you switch in the other direction, third and fourth. And so when you see very nicely this all-optical helicity dependent switching for light, you see the same thing for electrons. Again, here, this is above the compensation. This is below the compensation. And you can see this effect in both cases. And you see that the amount of energy that you have to put on is only 4 times bigger in the case where we are creating electrons and those electrons are doing the job. So clearly here, we could show this gadolinium and cobalt single pulse switching with hot electron pulses. So this is done after a long time after the reversal. We looked also at the dynamic, and you clearly see that we have the same kind of dynamic for the switching of gadolinium cobalt from 1 to -1 than with laser and with hot electrons. So we have the same kind of quasi-static switching. We have the same kind of dynamic. Again, what could be observed is that there's a delay, and this delay depends on the copper thickness. So we plotted here the delay and also the broadening. And again, we have this linear variation. And the linear variation that we observe is very similar to the linear variation that has been observed for the cobalt platinum demagnetization. All right. So here we come, and we can now say that this all-optical helicity independent switching can be observed for femtosecond electron pulses. And as Jeff shown yesterday, it can be observed also if the pulse duration is much larger for the electrons. Now, let's look a little bit at what we can do for those kind of materials. So in that case, what we have done, we looked at, this is getting much closer to Spintronics, because we looked at a spin valve. So we have a spin valve, gadolinium and cobalt on top, copper in the middle, cobalt platinum on the bottom. This copper thickness, we will see exactly the same effect if we go from a few nanometer to about 20 nanometer. We did the hysteresis loop at room temperature, and those minor loops tell us that there is no exchange coupling between the gadolinium and cobalt and the cobalt platinum. And this is very important, that we could observe no exchange coupling, and doesn't seem to be any dipolar interaction. And in this system, the interesting result is this one, is that with a single pulse, just a single pulse, you can go to the 4 different magnetic configuration, to the 2 parallel state, to the 2 antiparallel state, meaning that with one pulse, you can either switch the gadolinium and cobalt alone, or switch both and switch the cobalt platinum. So this is this first observation of cobalt platinum being switched with a single pulse and no coupling between those two layers. Okay, so let's try to look a little bit into the details. So we start from initial state here where the system is saturated, so both layers are pointing in the same direction. Then we send one pulse, a second, a third, and a fourth. And we look at different energy of the laser. So if the energy is low, then you only switch the gadolinium and cobalt, and indeed, you see this all-optical LCT-independent switching. But once you reach a certain fluence, then you see that in the middle, you go from blue to red, meaning that you go from those two aligned parallel in one direction to the two aligned parallel in the other direction. So we clearly observe the switching of this cobalt platinum. And of course, when you start with a high fluence, the intensity is much larger in the center of the beam than away from the beam. So this switching here is just the switching that was observed for low fluences. So we just did an analysis where we just suppose that we have a laser beam which is Gaussian, and we looked at the radius, so the distance between the center and this position here as a function of r squared pulse energy, and we could have this state diagram where you can see no switching. Of course, if you are far away from the center and the pulse energy is low, we can have the gadolinium cobalt switching if you have if you are not so far from the center, and if you are close to the center, then we do see the switching of both layers. Then we wanted to see what's important, and here I'm showing you we start with the 4 different initial states, and you see that the nice switching in the center appears only if we start with the 2 magnetization parallel. If we start with the magnetization antiparallel, you don't see the nice switching of the cobalt platinum. So it tends to tell us that the 2 magnetization at the initial state have to be parallel to each other. What we have done is, instead of having a gadolinium and cobalt with iron cobalt rich, we moved to gadolinium rich in order to see if what was important, it was the magnetization or the orientation of the gadolinium, for instance. And you see that if we go to gadolinium rich, this is totally inverted. It's only when you are in the antiparallel state of the magnetization that you do see the switching. So what's important is that you start your initial state, start with the gadolinium inside the gadolinium cobalt, antiparallel to the cobalt platinum on the second layer. You have to start with this initial configuration in order to observe the switching. And so basically our understanding is to say that we also have hot electrons that mediate the switching, and that those hot electrons are polarized by the gadolinium. And so this would be in accord with what has been published also this year, showing that the spin current is polarized by the gadolinium. In order to try to make sure that this is really mediated with the hot electrons, what we have done is we have inserted inside the copper some MgO in order to block those hot electrons. We also inserted some platinum in order to depolarize them. And what we see is that if we put some MgO, then that's it. You don't see anymore the switching. So if you block those hot electrons, there is no switching. And the total thickness is still the same, so you cannot, it has to be attributed to the MgO. For the platinum, that's a little, the story is a little bit different. The amount of switching depends on the platinum thickness. So it makes sense if we say that, okay, once the polarized electrons are going through the platinum, if it's not thick, if it's not really thick, it's going to be slightly depolarized. If it's thicker than 2 or 3 nanometers, then it's totally depolarized. So it looks like okay, in this case, the switching of the cobalt here is due to some hot electrons going from the gadolinium to the cobalt. So one question that we could ask ourselves, is it just happening in that case, or is it more general? Meaning that in this gadolinium iron cobalt alloys, in all our alloys, do we have some hot electrons going from the gadolinium to the cobalt? So in other words, where do we need this exchange coupling? All right, so what I think we have shown is that in here, you can also switch some cobalt platinum when you polarize those hot electrons, and even with pulses, there are a few femtosecond.
Sorry, but the laser pulse is not circular polarized.
Sorry?
The laser pulse is shining on the gadolinium on cobalt layer. Is it circular polarized?
It doesn't matter. In that case, we could observe it for a linear, for circularly polarized.
Only the hot electron generated is polarized, right?
Yeah. Yes, because of the gadolinium. Yes. So yeah. So that's not that. You're right. This is an important point. This is not the helicity of the light that will determine in which direction your cobalt platinum is going. This is the direction of the gadolinium here.
And that was an 80 nanometer copper. This one, 80 nanometer.
No. This is happening between 3 nanometer and 20 nanometer. And above 20 nanometer, again, we believe that we cannot see it, not because the electrons cannot go through. We have shown that it can go up to 200 nanometer, but they are not polarized anymore. So this is an important thing. So we have data from 3 to 20 nanometer. Okay, and then last thing I'm going to be talking about domain wall motion. It's not that we have done more with some electron pulses, is that here we have combined spin orbit torque and all optical switching. So you see here, we have 3 different cases. Electrons are flowing in that direction, and this is how much the domain wall has moved. And so we see that from one helicity it has moved a lot, for the other helicity it has not moved, and for this helicity it has moved a little bit. And this is circular in one direction for those, and the other direction, and this is linear here. What also important is that the intensity, the current is too low to induce any domain wall motion, and the light is also too low to induce any motion. So you need both. What we can see here is that it's a spin orbit torque, because the electrons are moving in one direction, the domain wall is moving in the other direction. We can see that heat is indeed affecting the system, because the linear, in the case of the linear case, we do see a motion here. But we see much larger motion for one helicity and no motion at all for the other helicity. And we reproduce that, and we basically now have a shot of how much you can put of current, how much the fluence of the laser. And it seems our calculations tend to show that it's energy efficient. So if you combine the energy received by the photons and the energy given by the electrons, then it's more efficient to combine the two than having only spin orbit torque. And so, and then what we have done is couple those two, and one more thing, there are many pulses here. So it's about 1,000 pulses in order to observe this. And then what we have done is combine spin orbit torque and all optical switching, and we did 3 types of measurements that you can see here, where we put a delay between the light pulse and the electron pulse. And of course, when the delay is 0, meaning that the electron and the current pulse is at the same time, you have much larger domain wall propagation than if you start to increase the delay between the two pulses. Yeah. And then, so finally, I think we were able to fill this shot, so we're done. We can see that what we did is we did observe this all-optical helicity-independent switching for light pulse and electron pulse. We observed all-optical helicity-dependent switching for light, and we have reduced strongly the number of pulses. We came up with a state diagram. This helped us to conclude that it seems that this inverse Faraday effect of this induce of magnetization is very important. And in some case, MCD cannot explain the result that we are observing. Of course, we totally agree that both effects exist. We could observe the switching of some cobalt platinum. So it means that any kind of ferromagnetic materials will be able to be switched by just one single pulse in this kind of spin valve geometry. So we are very close to some spintronic devices in that case. And we're also starting to have quite interesting results on dominant wall motion assisted by laser. With that, I have this extremely important slide. I had the chance to work with many different people, many different places. I would like to highlight Eric Fullerton. I could spend some time at UC San Diego. I'm working in Nancy with Gregory Malinowski, Jan Gorchon, and Michelin, and I could work with all those very nice people. And last, I have a slide, which is an announcement. So Andre is gone, I think. I just wanted to mention, as it was already mentioned, that we have a cost project. You can see from those working group that those are really the type of topic that we are discussing here. If you want to have more information, you just go on this webpage. And with that, I would like to thank you very much.